Welcome. Welcome, everyone. How's everybody's good morning? Or well, good morning, good afternoon, and good evening to everyone. I'm sure there's lots of people joining us from different places. I hope everyone's excited. It looks like we're just going to wait maybe 1 or 2 more minutes before I start my introductions. And I'm sure all of you can see Dr. McFarlane on the screen. I don't know, I'm pointing in the wrong place.
Hello.
But we'll soon get started. And let me see, it's right at 8:30, so I'll give more people if they were going to join a minute more. So I hope everybody's really excited because this is going to be a super fun presentation. If you're interested in chemistry as a future, or if you're just curious about science, this is the perfect place for you to be. I hope you guys get to learn lots. So I'm just going to start right off by introducing. I'm Janvi. I am the marketing coordinator at ICM, and I'm very happy to welcome you to our Spotlight Series number 3 with Dr. Shaune McFarlane of chemistry. Can I get a few clapping hand reactions? That would be nice. But just Dr. McFarlane. Dr. McFarlane has been teaching chemistry at ICM for the last 10 years. It's been a decade. Thank you so much for the decade of teaching. And today, Dr. McFarlane is going to talk a little bit about, imagine a world without chemical knowledge. What would it look like? No cell phones, no computers, no new medicine, no vaccines, etc. So Dr. McFarlane is going to be talking about how chemical knowledge is the foundation of all our materials. So hope you're looking forward to that. And a little bit about Dr. McFarlane. So Dr. McFarlane did his BSc in chemistry at the University of Winnipeg. Then he did his master's in chemistry from the University of Manitoba. So he's a fellow University of Manitoba alum, as hopefully all of you are going to be soon. And he did his PhD in chemistry at the University of Alberta. So, Dr. McFarlane has been at different institutions and has a lot of work under his belt. So, we can go from here. I'm going to stop rambling. So Dr. McFarlane, it's all to you. Take it away. I hope all of you have a great time.
All right. Thank you, Janvi. So there's lots of stuff I could talk about chemistry. Chemistry is, it's very broad subject. And so I picked something that I worked on when I did my PhD in chemistry. And so the title that I sort of picked today is called The Chemistry, Physics, and Engineering of Organic Light-Emitting Diodes. Now, how many of you have heard of OLEDs before? OLEDs, Organic Light-Emitting Diodes. You could say yes, or you could, let's check the chat box here. Yeah, you guys have heard of LEDs before? LEDs? So OLEDs are a little bit different than LEDs. The physics behind them is very similar, okay, except organic light-emitting diodes has to do with polymer or plastic type materials, okay? And so those of you that have a cell phone, if I show you my cell phone here, it's only been recently that you could have an OLED screen, okay? And one thing about an OLED, organic light-emitting diode, is that in contrast to other types of screens, typical screens will have a big light on the back, and then that light gets filtered out to generate the color that you want to see in a particular spot. Okay, whereas with an OLED, each little pixel is lit up. So wherever you see a black spot here, it's not actually being lit up. Okay, so they're very energy efficient. Okay, and so with the development of OLEDs, you then get the possibility of being able to actually have a cell phone that when you charge it with a battery could stay on for can be charged all day basically, okay? So here's just a picture of an OLED TV, and it's only been recently in the past 5 years or so that OLED TVs have actually come to market. And one of the problems that hindered the development of these OLED TVs or OLED TVs is the blue color, right? Now, so we're going to talk about, the visible spectrum and say Chem 1100, right? And so the low energy end of that spectrum is the red end, and then you get to the high energy spectrum, that's the blue end, okay? And the problem with the blue colors coming out of OLEDs is that they eventually degrade and you start seeing a green color, okay? And so my PhD, I worked on developing materials or new molecules that would be stable, that it didn't really matter what the environmental conditions were, whether it was high temperature or was being attacked by oxygen, that when you have a blue spot on your screen, it would stay blue, okay? I remember when I was working on my PhD from 2004 to 2008, in 2008, I saw, I looked at some reviews of these OLED TVs that were coming out, and you could buy a TV about this big that was like $2,000. Okay, so it was very expensive, right? And some of the reviews were that, well, it's a great TV, except that blue fades to green. Okay, so they still hadn't found the correct materials to generate a stable blue emitting material. And actually my PhD thesis, which is here, you can see that, right? It's like 250 pages, was on, it's called spectrally stable polyfluorine materials, okay? So these stable blue emitters. But first off, let's look at what the architecture of what an OLED is, okay? Let's see if I can move this. There we go, okay? So here's sort of the engineering of an OLED, okay? So down here, you have this piece of glass, and you can see that on the right, we have this piece of glass here, okay? And this is one of my first successful OLEDs that I created in the labs. You can see that it's glowing blue here, okay? This is, now sometimes we call it a PLED, a polymer light emitting diode, as opposed to an OLED, organic light emitting diode. So here you have a glass layer, and then this layer here, ITO, stands for indium tin oxide. Okay? Now in Chem 1110, we'll talk about anodes and cathodes. Okay? So the anode, okay, that's where oxidation will take place. And so you can see there's many layers here. So we have this ITO, which is called indium tin oxide. And so it's tin oxide, which is SnO2, that is doped with a little bit of indium, okay? And that makes it nice and conductive, almost like a metal, okay? And then on top of that, we put this layer called P.PSS. Now that's just another polymer, okay? And the way we put these materials on is we do what's called spin coating. So you take your glass substrate that's sitting over here, you put it in a machine and you spin it at about 3,000 RPM, and you drop your solution on it, and you can get a nice thin layer. And we'll get a chance to look at these thin layers as well. And so this layer here is really to smooth out this tin oxide surface, okay? And then the layer of interest that I was working on was this layer here, which I call PF. And I colored it blue because it's going to emit blue color. And so this is a polyfluorine layer. So this is, and we'll take a look at what that molecule looks like. And so that's what's called the electroluminescent layer. Okay. Now you might have heard of terms such as photoluminescence. You might have heard of phosphorescence. It's really the same thing. It's just that we are getting it to emit blue colors by applying a voltage here. Okay. And then on top of the polyfluorine layer, I evaporate some metal on top of there. Okay. Typically, I put a small layer of calcium, and on top of that, a small layer of aluminum, okay, on the cathode. Okay, so what happens is you apply a positive voltage over here, okay, and that pulls electrons out of this layer. Okay, so electrons are moving this way, okay, and the electrons move through the circuit, okay, and get injected into this layer. Okay, so now we'll also talk about in Chem 1100 semiconductors and other types of materials. And so when you're losing an electron from this layer here, we sometimes call that a hole. So it's a missing electron. So we can think of that the holes then are moving this way, and then the electrons are moving this way. And then when an electron, meets a hole, okay, what you end up getting is basically an excited state, okay? And then that electron will fall down into the hole, and based on the electronic structure of the PF material, okay, the energy gap there, okay, this is designed such that it will emit blue color, okay, in the blue part of the spectrum, okay? So there's lots of interesting physics and engineering to create these devices. I was a chemist, and I had to also learn how to make these devices. It took me about a year to actually get to making one of these successful devices. Yeah, it is amazing. That's why I love chemistry, right? It's like you manipulate molecules to do what you want to do, and you can create anything, okay? And so these phones here, okay, the colors that you see, every layer, it's inkjet printed. Millions of these things are inkjet printed on your surface, okay, layer by layer. Okay, so that's the engineering part, okay? Now, obviously, I made a big one so I could just test my material here, okay? So there's lots of physics and engineering we could talk about here, but it took me about a year to get this successfully working, right? Because to make these devices, you have to be very careful. So I had to take my glass substrate with the ITO on it, and I first had to wash it like in a sonicator 3 times, 30 minutes each, okay? Then I had to take it to a clean room and do what's called a reactive ion etch. You place it in a plasma to clean off the surface. Okay, lots of details I could get into, okay? And then carefully, quickly, within a matter of minutes, put this layer of P.PSS on, okay? Because without that layer, you're gonna get carbon from the atmosphere getting onto your surface and contaminating it, and the device won't work, okay? Then you could put the PF layer on and then your metal layer on, right? So it took me about a year, year and a half to get to this first successful device, okay? And I had to learn a lot of new things that I had never learned, say, in my chemistry course, okay? Different techniques, okay? But my chemistry knowledge came in useful, okay? Okay, so what do these blue emitting materials look like, their structure, right? So here I call, this is the blue emitting polymer, and the general name is polyfluorine. And it's not fluorine like the atom fluorine, okay? This unit here is called a fluorine unit, okay? And PFO is the standard workhorse polymer in this field. And it's called PFO because polyfluorine, and the O is the octal, okay? So these R groups here consist of these octane chains. So we got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this is a polymer. So this N here, okay, so long as it's greater than about 6, okay, you will get blue emission, okay, from that, okay. And so you can see this is a line bond structure of this. We talked about that in Chem 1100. We see pi bonds here. We see these pi bonds are delocalized. And so these pi bonds are delocalized along the entire chain. And we talk about delocalization of electrons and what that means in Chem 1100. Okay. So a lot of the stuff you learn in Chem 1100 and 1110, okay, are all of the basics to be able to help you understand what's going on in say this talk here that I'm giving now, okay? Now, the key problem with these materials is this point right here, okay? These are not very stable units, okay? And it doesn't take much for this to break off and you end up getting a ketone here, okay? And if you get a ketone there, this thing will now emit green. Okay, and so that was the main problem with these materials, is that this would eventually emit green, okay? Because these devices inside here, they can get up to 80 degrees Celsius, okay? And so you have oxygen diffusing in, and over time, your material degrades, okay? And so my PhD was focusing on making new materials that would prevent the formation of this ketone here, okay? Okay. So if we look here, and we'll talk in Chem 1100 about absorption and emission spectra. So here is an absorption and emission spectra of pure PFO, okay? So I would just buy this workhorse polymer, PFO, with the octal groups on it, okay? And test it to see how it behaved, okay? And so I would spin coat it, and then I would take a spectrum, an absorption and an emission spectrum. So over here we see these peaks here, that's the absorption spectrum of this polymer. So you notice that it's absorbing, you know, somewhere in the UV, right? So over here, this is the ultraviolet part of the spectrum, okay? Now to collect an emission spectrum, what I would do is I'd shine light on it, excite it in the UV, and then at 90 degrees angle, you could collect the emission as that electron came back down, okay? And notice the emission spectrum is at a longer wavelength, okay? So this would be the emission, okay? Whereas over here, this would be the absorption spectrum, okay? The absorption and the emission spectrum, okay? And so if you notice here, this emission spectrum, remember blue, right? So between 400 and say 700 nanometers, 400 is around the blue part of the spectrum, and 700 is around the red part of the spectrum. So notice that we're starting to get colors out of here that are in the blue part of the spectrum. Okay, so straight out of the bottle, now this material was quite expensive. I would buy 1 gram of this material. Okay, so 1 gram of this PFO material, okay, it would cost me $900. Okay, so I had to be very careful with it, and I bought a few grams, okay, to play around with it to see, how it behaved under certain conditions. Okay, and here is what happens. Okay, if I take this material, I spin coat it, and I heat it on a hot plate. Okay, so here's the absorption and emission spectrum of the PFO heated in air. So you'll notice that we still have a little bit of absorption here, okay? But you'll notice that we get this big green peak, okay? So it doesn't take much actually for it to emit green, okay? And that's a problem, right? So this is just to demonstrate that the workhorse polymer like PFO, polyoctofluorine, okay, emits this green color, okay? Now, what did I do to try to make new materials? Okay, so I developed a synthesis to make what are called aromatic ethers, because I knew those were stable bonds. Okay, so you start out with this material here that you could buy. Okay, and I undergo an oxidation over here. Okay, undergo an oxidation, and I'd actually purposely put a ketone in here. Okay. And then in step 2, what I would do is I would add molecules such as this. I'll just draw that in here, okay? This phenol over here, okay? And if I got the conditions right, I would then have this molecule over here where I now have this group now bonded to this position, okay? And then I have these 2 groups here that I could further attach other molecules to if I wanted to. But now what I've done is I've added an aromatic group here, which is more stable than having, say, an octal group, okay, in those positions, okay? Now, having these free OH groups here, okay, what I could do next is, now you won't learn about this chemistry in Chem 1100, but this is a strange type of bonding. And I actually learned this chemistry when I did my master's degree. So I took some of my master's knowledge, okay, and combined that with making OLEDs, okay? And so I was able to functionalize this oxygen here with another aromatic group, okay, over here, okay? And I could extend this as long as I wanted to, okay? Then in the next step, I'd use UV light, okay, to remove this iron group here, because I have to remove these after, okay? That was just there to help me do this reaction, okay? And then I could make this aromatic ether, okay? And so I made dozens of different molecules of this type, and I was able to test them, okay? Now, you want to be able to prove that you made something, right? How do you prove that? And there are different ways to do that, okay? The easiest and quickest way is to do what's called an NMR spectrum, okay? If you've ever been to the doctor and you've taken an MRI scan, okay, they call it MRI as opposed to NMR. NMR stands for nuclear magnetic resonance. MRI stands for magnetic resonance imaging, okay? Really, it's NMR, but they call it MRI because no one likes to go into a machine that's called NMR, nuclear magnetic resonance, but it's the same thing. It only uses radio waves, okay? Now, if you get further into chemistry, you'll learn how to use that technique to actually detail atom by atom what the structure of your molecule is. You'll be able to tell that I have a carbon bonded to a carbon here. I have a carbon-carbon single bond here. I have a carbon-carbon double bond here. You'll be able to spell out in detail the structure of your molecule, okay? Now, another way you could determine whether you've made the structure is to grow a crystal of it, okay? So in Chem 1110, we'll talk about X-ray crystallography. And so here's a picture. I was able to grow a crystal of one of these molecules, right? And so this is the actual data, the crystal structure of one of the molecules that I made, okay, to be able to grow this, okay? So you just like you would grow salt crystals, right, type of crystals, but you got to get the conditions right, the intermolecular forces right. So I was able to grow a number of crystals for my various molecules that I made, okay? And so you can see here, this is the benzene over here. Here's an oxygen, a benzene, an oxygen, a benzene. And this is the fluorine unit that when I join a bunch of these together, we'll be able to make a blue emitter. Okay, and so again, we move this up, we have a benzene, oxygen, benzene, oxygen, benzene. And again, we have this point of connection here. Okay, so I was able to make these molecules using knowledge that I had learned previously from my master's degree and apply it to a new field, right? And that's one thing you want to do is any knowledge you learn in any course, you can always apply that to a new field or something different, okay? So let's see here. Okay, now here's another structure of another molecule that I actually made by accident. I had a theory that I would make something with the particular molecule I was using, and it took me about 6 months to actually figure out what I had, okay? And so I made something that was very unique. This is what's called a xanthine containing fluorine monomer. And one thing you'll notice is that it's hard to see here. We have the fluorine unit over here, okay? And then my aromatic groups have sort of formed a ring on themselves like this, okay? Yeah, so you guys will be learning everything from the basics, right? So I want to just give you an appreciation for, you know, where you could get to in chemistry, right? And all the interesting things you can do, right? You can pretty much make anything, right? That's why I love chemistry. It's the power to understand how you can make anything, right? It's like with these vaccines that came out, it's all about chemistry, right? Viruses, I think of viruses as really supramolecular molecules, right? The viruses aren't really living, okay? They're really just giant molecules that are able to self-replicate when they're inside a host, okay? And so if I look over here, I can get a picture of actually how they pack in the solid state, okay? And so you can see here, you get these little X's, right? So this is the molecule, and they're packing. So you can get an inside picture of how they're packing and what the intermolecular forces are holding them together, right? In Chem 1110, we talk about intermolecular forces, the basic types, right? Right? We won't be doing anything this advanced in Chem 1100 or Chem 1110, but if you're in my class, you can, you know, if you remember this lecture or this talk, you can, you know, obviously ask me. And sometimes I bring this in just to illustrate, you know, some of the interesting things that you can do in chemistry with the knowledge that we're learning, okay? Now, in order to take these individual molecules and then be able to couple them to make a polymer, okay, with these types of molecules, there are basically three different methods. One is called an oxidative coupling, where you take iron chloride. That kind of leaves a lot of defects, right? Now, I initially started out using Yamamoto coupling, okay, where you just have, at the end of your fluorine units, you'll have just the bromines on the end, and you add a nickel catalyst, okay? And then I switched to what's called organometallic cross couplings called Suzuki. Okay, these guys have won Nobel Prizes for their ways of coupling. And in that case, I have to actually change the bromine into this unit here in order to make polymer, okay? Yeah, so the monomers are the smallest units of a polymer, right? And so my first big job was to try to make these stable, these various monomers. And then once I make these monomers, then I can make these polymers, okay, in the last step, okay? The chemistry part of it, okay? Now, here is an example, a picture I took of one of the polymers that I made, okay? And so you can see here that you can see the film, right? So you want to be able to have a nice film if you want to have it on a surface, right? And so I just let it evaporate and then the film form. And I placed it under a UV lamp just to see if it would glow blue. And you can see that it does indeed glow blue, right? So at least I'm successful at that point, right? So it can glow blue, okay? Now, this was actually a year into it. And this is just PFO. I'm trying to make my first device, okay? And I caught this just for a brief second, okay? I call it successful here, but it really wasn't successful, okay? So what you see here, this is called a electroluminescence plot or a photoluminescence plot, okay? So here I'm plotting current in milliamps as a function of voltage, okay? So typically you want your OLED to turn on at around 5 volts, right? You don't want to consume too much power, okay? So one thing you'll notice is my OLED turned on at a high voltage initially, okay? And you can see there's a lot of black spots in here, okay? So not very good, okay? So I wasn't very skilled yet at being able to precisely make these devices, okay? But eventually I was able to, which you saw in that first picture. Okay, now take a look at a cross section of these devices, of my failed device. Okay, here's a cross section. So I took a look. And so you take the device, you break it and just snap it in half, and then you take what's called a scanning electron microscope image, so SEM. So you use electrons to image. Okay, and we'll talk in Chem 1100 about the wavelength of electrons. Okay, and so we can make matter have a wavelength just like light, and so we can use it for vision, okay? And the wavelength of electrons can be much smaller than light, so we can see smaller things. I cannot see this with my eyes. I have to use electrons. So you see here the scale 100 nanometers, okay? So here is the glass surface that it's on. Here's the indium tin oxide, the tin oxide layer, and here's the P.PSS layer, okay? So on the side view, it looks good. And you can see it looks to be about maybe 75, 70, 50 nanometers thick, okay? So very thin, okay? And I look at a oblique view of it, I see it looks smooth and good surface coverage, okay? And then I spin coat my polymer on top of that, in which device it contains. So this is the OLED. So I'm trying to make an OLED here. So it's kind of like, if you look back to the beginning, if I go back to here, let me go back quickly. Okay. So you're looking at the ITO layer, the real ITO layer, the glass layer, and the P.PSS layer. Okay. Next, I'm going to show you the PF layer, okay, and we'll see what that looks like in that device that didn't work very well. Okay, so I take a look. Go back here. Okay. So the P.PSS looks smooth, nothing really wrong with it. Okay. But then when I've actually put my polymer on top of it, and I take a look. So over here is the P.PSS. Okay. And this stuff coating on top, that's my PF. Okay. And notice it's full of holes. Okay. And I was like, oh my God, that's not good. Okay. So that's why it wasn't working. Okay. Now, to make a long story short, I eventually realized that the solvent that I was using for spin coating had a minor trace of water in it. So I had to do distillation and get rid of all the water out of the solvent. And then in the end, I was able to make these nice smooth films. Okay. My theory was that the water droplets were then not evaporating as fast as the solvent. So therefore, these kind of are imprints of water where the polymer couldn't coat on in various spots. Okay. So this is an SEM image. And I also took what's called atomic force microscopy images of the surface. Okay. Now AFM is similar. It's AFM is you can Google that. You can look at all kinds of interesting things. So here's an AFM image of that surface. You can see the holes, and with AFM you can see that it looks pretty deep, right? The holes that are in there. Okay. And so we can also do a plot across here showing what the height is at various points along here. Okay. Notice the scale here is nanometers. okay? Now remember, a hydrogen atom is equal to about 0.1 nanometers. So if you have 10 hydrogen atoms, you're looking at 1 nanometer, okay? So you can use that scale to figure out, how many atoms tall are these cliffs that are here, right? In terms of hydrogen atoms, if you like, okay? So if we look and trace out that plot there, you can see that, 10 micrometer, right? And so if you look at this plot here, height here in nanometers, right? So here's 0 point, okay? So across there, I'm up 50 nanometers, up a little bit more, not very smooth yet. Then I get deep in the hole there. I go down about how many nanometers? 150, 50, I'm 200 nanometer hole there, okay? And the reason the device didn't work and didn't last is I would get a short, okay? You'd have a short circuit now, as opposed to the electrons going through here, they would go through here, okay? And that would be a problem, okay? And here's a three-dimensional image, AFM image that was done, okay, of a surface where we had that problem, okay? So just so you can see that, okay? So the further you advance into chemistry, you can use all kinds of different techniques. These days, you can actually look at individual atoms and individual molecules, right? Nobel Prize was won because of that, okay? Yeah, fluctuations. Yeah, lots of fluctuations because you're dealing with, you got to think of the scale you're dealing with, right? These fluctuations, I believe this was due to the fact that there was water in my sample, right? And then later on, I ended up getting a nice smooth surface, and my devices worked fine once I removed the water from it, okay? And then when I did an ICM image of it and an AFM image of it, it was practically smooth, okay? Maybe 1 or 2 nanometers up and down like this, so very smooth, okay? And so here's a side-on view of the device, okay? A side-on view. So I removed the water. So you add a drying agent to the water. So you might add sodium metal to the water to remove some of the water, and then you would distill your solvent as well, okay? So the sodium would react with the water, remove some of the water that way, and then also do a distillation to purify the water even more, okay? And once I did that, it started to work, okay? I actually, wrote out there was a 13-step process to actually getting to make this device work, right? In every detail mattered. And that was the engineering part of it. And being a chemist, I was like, well, the engineering part, that's going to be easy, right? But no, okay? That took just as much work as the chemistry part, okay? And so here you can see a device where I have the glass here. And here's the scale, 100 nanometers. Here's the ITO. Okay. Here's my thin layer of P.PSS. Okay. Here's the PFO. This is the fluorine-based one. Here's my PFO here, my blue emitting material there. And here's my calcium and my aluminum evaporated on top of that. Okay. That's the side-on view. Okay. Now, there are other properties besides that we've been talking about so far that are important for OLEDs. Okay. And, right away in Chem 1100, we're going to talk about heat flow and stuff, right? And so over here, I did a plot of heat flow as a function of temperature on my various materials. And what you'll notice here is that as I raise the temperature, right, these polymers, you'll get a decrease here, and then it goes flat over here again. And different ones have called different TGs. They're called glass transition temperatures. Now, they're called a glass transition temperature as opposed to a melting temperature, because melting is really about crystalline substances, and these polymers are not crystalline. It's really a place where you have, it's called a glass transition temperature because if you've ever taken something that's plastic and it's kind of rubbery and you place it in the cold snow and it gets cold, and then you smash it against something, it'll break, it'll become brittle. Okay, so the temperature at which it goes from being rubbery to being glassy, that's called the glass transition temperature. And that's important for these devices because other aspects that I can't get into in this course is that as this heats up, the polymers could move around, and that could also change the emission. Okay, there's many factors that could change the emission, which makes this exciting because many things you can control. okay? And so I made materials with different glass transition temperatures, right? So if you could get a glass transition temperature that was, greater than, 80 degrees Celsius, which was the device temperature, then you have a chance that it's not going to become rubbery. It'll stay firm throughout the operation of the device, right? And so these are significantly high glass transition temperatures, so they're pretty good. 85 is good. 91 is a good glass transition temperature, so it's 108. Okay. Now, another parameter you want to measure is, well, how stable is it? So remember, the PFO is the ones with the octal chains. Okay. So here we do what's called a TGA, thermal gravimetric analysis. So you take a few milligrams of sample and you weigh it. So that's the weight initially, right? So we say it's 100%, okay? And then you heat it to a high temperature, okay? You vary the temperature. And then you measure the weight loss. Is the molecule falling apart? And so the mass of the balance will decrease over time. So you notice that the PFO starts degrading at a lower temperature, okay, than the new types that I created with the aromatic ethers, which start degrading at a higher temperature, okay? So that tells me that these molecules are more stable than the PFO and are less likely to emit green light, okay, and produce a ketone, okay? So by just changing the two groups in that position, in the fluorine molecule to something different that's more stable, you can create a new material. But of course, changing that can also cause other problems. So you have to manipulate, there's all kinds of things that can change. So this red line here is the one that shows mine, okay, one of mine. And all of mine were always higher than the PFO. So it's a higher temperature to degrade. PFO is this guy here. If I go back, let me go back to the beginning quickly. Sometimes I try to say too much and I should maybe say less. So this guy here, PFO is the one with the octal chains in this position, okay? So I changed these octal chains to these ether chains instead, okay? So if I add these, they become more stable. The polymer becomes more stable, okay? But it still emits blue light. So these side chains have no effect on the blue color, okay? Go back here, let's see, okay? And now, of course, the big test is, remember when I heated the PFO, I had this big green peak show up here, okay, the big green peak, okay? I did the same thing with my materials that I made it. I heated to various temperatures, and I would never see that green peak being formed, okay? There was no ketone being formed, okay? If we look back, PFO, which is, did I show that here? Yeah, here it is, right? PFO under the same conditions, heating and air, right? I get this big green peak showing up, okay? Whereas you change it a little bit, okay? There's no green peak, okay, which is good, okay? No green peak, which is good, okay? And so here is now the picture of the good devices. And after a while, now notice on here, I created 1, 2, 3, 4, 5, 6 devices on here, okay? And so I can light up each one of these individually. This is the one I lit up at this time, okay? And there's a special machine that actually will collect the light, analyze it for you, figure out, what the efficiency is, all types of things you can work on. And so notice now that this is called the turn-on voltage is now lower, right? So it's now around 5 volts. And I got to the point where I could pretty much get 99% of all my devices to light up and not have any failures, okay? And that was after a couple of years, right? Once you master and get down the technique of doing this. Okay, so that's all I wanted to say about that. I hope I didn't. If you have any questions, please ask. I could have went into more detail on each area, but I just wanted to give you a big overview of what chemists are doing to make new materials and make your life easier. Okay, thank you.
Thank you, Dr. McFarlane. If anyone has any questions, so from the chat, I can see it's been quite lively and a lot of students were enjoying it a lot. So thank you, Dr. McFarlane. That was amazing. If anybody has any questions, we have about 10, maybe we can have some questions for 5 minutes.
Or anything you would like, in a future series, anything you'd like to know more detail about, that you would like to go into more detail at some point?
Just looks like everybody seems to have their mind blown, and it looks like everybody wants to say a big thank you to you,
Thank
Shaune.
you. Thank you.
Any questions asked now? Last call for any questions. So this is kind of what chemistry will look like when you eventually come to ICM and U of M. Please correct me if I'm wrong, Shaune, please.
Yeah, chemistry is beakers. Like people think, chemistry is beakers. I had to work with beakers and that type of stuff, but chemistry today is we learn these basic principles of UV vis, bonding, and I try to connect that to modern things that chemists are looking at today, especially in terms of materials chemistry, because chemistry is I had to work with physicists, engineers. It's a very multidisciplinary field now to be able to make these new materials. It's not just titrations. Yeah, you'll learn about titrations, but always bear in the back of your mind that you can use this sometime if you want to go further into chemistry when you do more interesting things.